Have you ever wondered what a star does when it isn't exploding or collapsing? Most of its existence is quiet, not dead, not frozen, just steady. Deep inside, atoms fuse and light escapes, second by second, for millions or even billions of years. Nothing dramatic, no fireworks, yet this long calm defines everything we see in the night sky. The steady burn of stars sets the color of galaxies and the chemistry of planets, including ours. It's a kind of stillness that hides enormous motion. In today's episode, we'll trace that quiet life, how a star holds itself together, how it shines, and how it finally changes form. If you enjoy slow, careful science told clearly, a small like and subscribe helps this light reach a bit farther. Settle in. The calm part of the cosmos is waiting. What does it mean for a star to live? From far away, a star can seem timeless, the same point of light every night. That is only the surface. A star has a start, a long middle, and an end. It changes size, temperature, and brightness as it uses fuel and reshapes its layers. The matter in our bodies, carbon, oxygen, and some of the iron in our blood came from earlier stars that burned, changed, and returned material to space. Learning how a star lives is another way to learn how galaxies and planets came to be, and how the ingredients for life were made and mixed. The pace is slow, but steady. A star begins in darkness, spends most of its life in a calm burn, and finishes by cooling or by shedding matter in more dramatic ways. The steps follow clear rules that we can describe with a few ideas and measurements that makes this a good subject for careful attention at an easy pace. The first setting is a molecular cloud, often called a stellar nursery. Despite the soft name, these clouds are huge. Many stretch for dozens or even hundreds of light years. They are made mostly of hydrogen gas, with helium mixed in and a trace of heavier atoms and tiny solid grains we call dust. Seen against a bright background of stars, a cloud can look like a dark shape that blocks light. In deeper views, you see long lanes, knots, and pillars, sculpted by radiation and wind from nearby hot stars. Inside the cloud, the gas is very thin by human standards. You could travel a long distance before hitting a single molecule. Because the cloud is so large, the total mass is still high enough to build not just one star, but many. Temperatures are very low, only a few tens of degrees above absolute zero. At these temperatures, hydrogen pairs up into H2, which is why we call these molecular clouds. Low temperature slows motion and helps gravity gain control. Gravity works quietly. Small pushes from outside, a shock wave from a supernova, pressure from nearby hot stars, or the slow tidal pull of passing clouds can raise the density in parts of the cloud. Slightly denser regions attract more gas, which makes them denser still. The effect feeds on itself. Over millions of years, some patches contract into dense cores. From far away, this looks like nothing at all. With radio telescopes, astronomers detect molecules such as carbon monoxide and ammonia. These molecules emit light at radio and microwave wavelengths, which pass through dust, so we can map structure inside the cloud. In some regions, we also find simple organic molecules, which shows that chemistry begins early, even before stars form. Dust has a quiet but important role. Each grain is a tiny bit of carbon, silicate, or ice, sometimes no larger than smoke. Dust absorbs and scatters light from outside. That keeps the inside of the cloud cool and stops it from breaking apart. Dust also provides surfaces where molecules can form and stick. In this way, dust acts like both insulation and scaffolding. Pictures from space telescopes make these regions familiar. The pillars of creation in the Eagle Nebula are tall columns of gas and dust shaped by nearby massive stars. The columns are light years long, and at their tips, small, dense globules hide new stars. These images are not only striking, they guide us to places where collapse and heating are active, so we can test our models against the sky. Time at this stage is hard to imagine. A human life might last about a century. A dense core can take 1,000,000 years or more to collapse. Change is real, but slow enough that we need patient surveys, returning to the same region again and again to see motion in outflows or warming dust. The right way to picture this is not a single before and after, but a set of snapshots of many objects caught at different steps along the path. As contraction continues, the core's potential energy turns into heat. Potential energy is stored energy due to position. Gas falling inward picks up speed, particles collide more often, and temperature rises. Pressure rises too, because pressure in a gas depends on how often and how hard particles strike their surroundings. Gravity pulls inward. Pressure pushes outward. The two set the pace of collapse. If pressure could not respond, the gas would fall to a point. Instead, the collapse slows and spreads over time. The object at the center is a protostar. It is not yet a true star because nuclear fusion in its core has not started. It shines mainly in the infrared because of heat from infall and compression. Around it, a rotating disk forms. The reason is angular momentum, a measure of rotational motion. Even a cloud with a tiny initial spin speeds up as it contracts, like a skater who spins faster when pulling in their arms. Material that cannot fall straight in settles into a flat disk. Later, that disk can be the birthplace of planets. For now, it is a reservoir that feeds the growing star. The flow from disk to star runs along magnetic fields that act like rails. The inflow is not perfectly smooth. It can surge, then rest, then surge again. During some phases, narrow jets of plasma shoot out from the poles at high speed. These jets can travel for light years and light up nearby gas, making small glowing patches known as Herbig-Haro objects. Outflows carry away angular momentum and let the central object grow in a controlled way. They also punch holes in the surrounding cloud, letting some radiation escape. Inside the protostar, density climbs to values with no everyday match. At high temperatures, atoms lose their electrons, and the gas behaves like a charged fluid called plasma. Heat flows outward from the center by two main methods. In some layers, energy moves as radiation, which is light carrying energy step by step through matter. In other layers, energy moves by convection, which is the bulk rising and sinking of hot and cool gas. Which method dominates depends on the mass of the protostar and the structure of its layers. But the basic picture is simple. Gravity supplies energy. The gas carries that energy outward. Star formation rarely gives a single object. A collapsing cloud usually breaks into many fragments. Some fragments will become massive blue-white stars. These are very bright and short-lived, often lasting only a few million years. Others will become medium-mass stars like the Sun, which burn for billions of years. Many will be small red dwarfs that shine faintly, but can last longer than the current age of the universe. The overall mix has a pattern measured in young clusters. Astronomers call it the initial mass function. It tells us that low-mass stars are common, while high-mass stars are rare. The cloud environment shapes how many stars form and how fast. Hot stars nearby can erode a cloud with their radiation. pressing on the edges and triggering new collapses, while also eating away at the gas supply. Supernovae can both compress gas and blow it apart. Magnetic fields threaded through the cloud can slow collapse by guiding particle motion and adding support. Turbulence, random, swirling motion can create dense pockets and also stir them apart. The final result depends on the balance of these influences. From the outside, a developing system is dim, invisible light because dust blocks the view. Infrared and radio waves pass through dust more easily, so telescopes tuned to those bands are our main tools. They measure temperatures, speeds, and chemical makeup. A small shift in the frequency of a molecular line reveals motion through the Doppler effect. Wavelengths stretch if gas is moving away and shrink if it is moving toward us. With these tools, we can see rotation in disks, gas falling onto stars, and jets cutting channels through clouds. As the protostar grows, its core temperature climbs. Hydrogen nuclei, single protons, must collide fast enough and close enough to fuse. Fusion means two light nuclei join to make a slightly heavier nucleus, releasing energy. For stars like the Sun, the key set of reactions is called the proton-proton chain. In more massive stars, another route called the C-No cycle dominates. It uses carbon, nitrogen, and oxygen as helpers to speed fusion. The exact details can wait. The key point is that once the core reaches the right temperature and pressure, fusion begins, and the star has a new, steady power source. Before that moment, the young object follows tracks on a diagram astronomers use called the Hertzsprung-Russell diagram, which plots brightness against temperature. As a contracting object, it moves along paths known as Hayashi and Henye tracks. You do not need the names to keep the idea. We can predict how a young star's temperature and brightness should change during contraction, and observations match these predictions well. Not every core reaches full stardom. If the mass is too low, below about 8% of the Sun's mass, the center never gets hot and dense enough for sustained hydrogen fusion. The result is a brown dwarf, larger than a planet, but smaller than a star. Brown dwarfs glow faintly from leftover heat, and, if massive enough, from brief fusion of deuterium, a heavy form of hydrogen. They fill the space between planets and stars and remind us that nature does not draw sharp lines. The early environment also sets the stage for planets. Dust grains in the disk stick into pebbles. Pebbles grow into larger bodies. Gravity helps those bodies merge. Far from the star, where it is cold, ice adds mass and helps build the cores of giant planets. Closer in, rock and metal dominate. While planets are not our focus here, the disk, the jets, and the clearing of gas are all parts of one system. A star forming at the center while the surroundings take shape. As a forming star pulls in the last of its fuel, it must also shed the spin that would otherwise choke growth. Angular momentum can't vanish, so the system moves it outward through the disk and flings it away along magnetic field lines. That's why jets appear, twin, narrow outflows from the poles that carry matter and momentum into space. They are not noise. They are the release valve that keeps the center stable and able to keep accreting. With spin bled off and infall slowing, the thick envelope thins. The young star's light and wind push back the remaining gas and dust, carving cavities through which radiation can escape. The region clears. The star steps from infrared into ordinary light. It is still young, still spinning fairly fast, but now visible as a single, growing source. Ahead, lies the longest, quietest, chapter core fusion holding gravity in check. That calm rests on everything before it. Slow cloud cooling, gravities gather, dust shielding, disk formation, the conversion of fall into heat, and the jets that made space for the star to emerge. The pace is slow. From the first slight collapse in a cold cloud to a stable protostar can take millions of years. Human history fits inside a small slice of that. It feels long to us, yet in galactic terms, it is routine. The physics is familiar, only bigger. Compressing gas raises its temperature, the way a bike pump warms in your hand. Rubbing your palms together turns motion into heat. Gravity does the same work by pulling gas inward for a very long time. As the protostar gathers mass, its light and warm gas push back on the material still falling in. Heating raises pressure, and pressure slows the inflow. A temporary balance emerges. Gravity pulls inward. The glow from the hot gas pushes outward. The object is not yet a true star because fusion has not started, but it has a size, a surface, and a clear boundary from its parent cloud. It is now a body with its own energy source, gravitational energy turning into heat. Whether the center will ignite depends mostly on mass. A small core may heat up, but never reach the temperature and pressure needed for steady fusion. Such an object becomes a brown dwarf. It shines faintly from leftover heat and, if heavy enough, from brief fusion of deuterium, a heavy form of hydrogen. A more massive core keeps contracting until the conditions are right to fuse ordinary hydrogen. The scene around a young protostar is organized by rotation. Even a very small initial spin speeds up during collapse. Material that cannot fall straight in settles into a flat, turning disk. This circumstellar disk is made of gas and dust. Dust grains collide and stick into pebbles. Pebbles grow into larger bodies. Close to the center, the disk warms and glows at infrared wavelengths. Farther out, it stays cold and shaded. Spirals and rings can form when turbulence, pressure waves, or growing clumps rearrange material. While the star is still forming, the early steps toward planets are already underway. The disk and the jets interact. Magnetic fields thread the disk and connect to the protostar. Gas sliding along those fields can be redirected and launched from the poles at hundreds of kilometers per second. Where the fast gas slams into slower gas around it, shock waves heat the material and make it glow. Telescopes see these glowing knots as Herbig-Haro objects. They can trace the path of the jets for light years, marking a long, straight channel carved through the cloud. Inside the protostar, the center grows denser and hotter. At these temperatures, atoms lose their electrons and the gas becomes plasma, a charged fluid. Energy moves outward in two ways. In some layers, light carries it by many short steps, being absorbed and emitted again and again. In other layers, hot gas rises and cooler gas sinks. This is convection. Which process dominates depends on mass and composition, but the core idea is steady. Gravity powers the heating. The gas carries that heat outward. As the temperature passes a few million degrees and climbs toward about 10 million degrees, the chance that two protons will get close enough to fuse rises. Protons repel each other because they are both positively charged. At high temperature and pressure, rare close encounters happen. The set of reactions that turn hydrogen into helium is called the proton-proton chain in stars like the Sunday. In more massive stars, the C-No cycle uses carbon, nitrogen, and oxygen as helpers to speed things up. Both routes produce helium and energy. Fusion does not start like a spark in dry wood. It ramps up. A small fraction of protons fuse, which releases energy, which helps hold up the core against gravity, which slows the collapse. The young star can overshoot and undershoot this new balance at first. It may puff out a bit, then settle, contract a bit, then settle again. These adjustments can last thousands of years. On the outside, it may flicker in brightness. On the inside, it is finding a stable point between inward pull and outward push. We know this stage well because dust does not block infrared and radio waves as strongly as visible light. Telescopes that work at those wavelengths can look into star-forming regions such as the Orion Nebula and count many protostars at different steps along this path. Molecules in the gas emit at specific frequencies. If those frequencies are shifted a little higher or lower, we can tell the gas is moving toward or away from us, the Doppler effect. That lets us measure rotation in disks, infall toward stars, and speeds in jets. Not every collapsing core makes a single star. Fragmentation is common. Groups of stars form together, often as binaries or small clusters. The spread in mass follows a pattern called the initial mass function. Low-mass stars are common. High-mass stars are rare. The environment shapes the results. Radiation from nearby hot stars can erode a cloud and also compress it. A recent supernova can both stir gas and trigger new collapses. Magnetic fields can slow contraction and channel flows. Turbulence can gather gas into pockets and break others apart. The mix of these effects decides how many stars form and how they are spaced. Once the core reaches stable fusion, the system changes category. Gravity pulls inward. Pressure from fusion pushes outward. The two are equal on average. This state is called hydrostatic equilibrium. The star has arrived on the main sequence, the long middle of its life. The surface temperature and color now reflect mass and composition. Hotter, more massive stars look white or blue. Cooler, low-mass stars look orange or red. Hydrogen fusion is simple to state. 4 protons, through several steps, become one helium nucleus. Because the helium nucleus is slightly less massive than the 4 protons put together, the missing mass shows up as energy. Einstein's relation, E equals mc, 2 tells us how much. The speed of light squared is a huge number, so even a tiny mass difference produces a large amount of energy. That energy leaves the core as high-energy photons and as neutrinos. Neutrinos pass out almost without interacting. Photons do not. A photon's trip from the core to the surface is not a straight line. The interior is dense. Photons are absorbed and re-emitted countless times. Their random walk can take hundreds of thousands of years. By the time energy reaches the surface, it has shifted into the visible and infrared bands. When you feel sunlight, you are feeling energy that began its journey long before any human record. The delay does not change the star's steady output because the core keeps producing energy at nearly the same rate, while the outer layers act as a reservoir and regulator. Inside, the mode of energy transport depends on mass. In stars like the Sun, the core is radiative and the outer layers are convective. Big cells of gas rise and fall, leaving patterns on the surface such as granulation and, with magnetism, dark sunspots. In higher mass stars, radiation carries most energy outward. In very low mass stars, convection can dominate through almost the whole star. The details vary, but the outcome is regular. A near constant flow of energy to space. That regular flow makes worlds habitable. A main sequence star does not jump in brightness from year to year. It changes very slowly, giving planets time to keep liquid water, stable air, and long-lived ecosystems. In a universe with many violent events, collisions of black holes, bursts from dying stars, the main sequence is a calm baseline. Lifespan depends mainly on mass. More massive stars have more fuel, but they burn it much faster. A star tens of times the Sun's mass can live only a few million years. It burns hot and bright and ends early. A small red dwarf uses fuel so slowly that it can shine for trillions of years. Beyond the current age of the universe, our Sun sits in the middle. Its main sequence lifetime is about 10 billion years. Roughly half of that has already passed. A forming system carries hints of its future. A heavy protostar with a thick, hot disk will likely host a different set of planets than a light one with a cool, thin disk. Strong jets can clear gaps and alter where material gathers. The chemistry of the disk, how much water ice, carbon-rich dust, or metal content, affects what kinds of solids build up. While planets are a separate topic, they are tied to these early steps. Star and system grow together. As fusion steadies in the core, some habits of youth linger. Outflows keep running for a time, then fade as the disk thins and the magnetic field reshapes. The wind drags on those fields and carries spin away, so the young star slows. Early on, surface activity can be strong flares, and bright patches rise and fall. Then it calms as rotation eases. Through it all, the core stays plain and reliable, turning hydrogen into helium. From here, the rules are simple. Gravity pulls inward. Energy from fusion pushes outward. While hydrogen lasts in the core, those forces balance, and the star changes only slowly on human timescales. Details vary with mass, but the main sequence story is steady work. Fuel in the center, light from the surface, structure adjusting gently to keep the balance. You can read some of this at a glance. Star color is a temperature code. Hot, massive stars look blue-white. Cooler stars glow orange or red. Stars like the Sun sit in the middle with a soft yellow-white tone. Color ties to surface temperature, which links to mass and pace of life. A single look at the sky is a survey of many temperatures and lifetimes at once, from fast blue burners to long-lived red embers. Calm does not mean static. In the core, hydrogen fuses into helium, so the mix of elements slowly shifts. Helium is denser and gathers at the center. The core must run a little hotter and denser to keep the same output, and that makes the whole star brighten over time. Earth's sun is a clear case. It shines roughly 30% brighter today than when life first took hold on our planet. No one notices from one generation to the next, but over geologic ages that change matters. During this long middle, stars shape their surroundings. Their light sculpts nearby gas clouds. Their steady wind of charged particles pushes on dust and carries magnetic fields far from the surface. Their gravity locks planets into orbits where climate can settle and chemistry can build. Heavy elements from older stars, carbon, oxygen, silicon, iron, are recycled into new clouds and new systems. Many of the atoms in a living cell were made in stars and spread by dying ones, then gathered again into planets and oceans and air. Time feels different here. 1,000 years is a blink for a main sequence star. To call a star middle-aged often means it has already burned for about 5 billion years and may burn for a similar span again. That scale can feel abstract, yet its results are personal. The oxygen in each breath, the calcium in a bone, and much of the iron in blood all trace back to furnaces in earlier stars. Daylight at a window is the quiet end of a large process that turns mass into light and sends it outward with near constant power. The main sequence is endurance set by fuel and gravity. A star in this phase is not hurrying toward an ending or stuck at a beginning. It is holding balance, gravity inward, pressure from fusion outward. Most stars spend the bulk of their lives here, converting hydrogen into helium and releasing energy at a steady rate. That steadiness gives planets time to cool, oceans time to stay liquid, and ecosystems time to develop. Deep inside, the story of light starts with a single act of fusion. 4 protons, through a chain of steps, become one helium nucleus. A tiny bit of mass is missing. It appears as energy. The core is a hot, dense plasma nuclei and electrons moving fast. A photon born there does not shoot straight to space. The interior is crowded and opaque. The photon is absorbed, re-emitted, and scattered in new directions again and again. Its path is a random walk, a slow zigzag with no direct lane out. Because of this, outward progress is very slow. If the star were transparent, light would cross it quickly. Instead, the diffusion time is hundreds of thousands of years, and for some paths, even longer. By the time energy has worked its way to the surface, the original high-energy gamma rays have been stepped down into lower-energy light. The final visible photon is the descendant of many exchanges, like a message passed through a vast crowd. One photon's path is uncertain, but the combined flow is steady, which is why the star's brightness looks so constant from far away. At the visible surface, the photosphere, the rules change. The mean, free path grows long. Photons escape into space and travel in straight lines until they meet matter again. From the Sun to Earth, that trip takes about 8 minutes, across roughly 93 million miles. Compared to the slow crawl inside the star, the last leg is almost instant. Light from the nearest star beyond our system takes a little over 4 years to arrive. Light from the Orion Nebula takes on the order of 13 to 1500 years. Light from the Andromeda Galaxy takes about 2.5 million years. A night sky is a layered record of many pasts reaching us together. Starlight carries detail. The mix of colors reveals temperature. Fine, dark lines in a spectrum. Absorption lines show which elements are in the star's outer layers and how hot and dense that gas is. Slight shifts in those lines show motion. If the lines slide toward the blue, the source is moving toward us. Toward the red, it is moving away. With these tools, astronomers read rotation rates, surface gravity, and even the small pulls of unseen planets that make a star wobble. Stars are not only lights, but engines. Fusion in their cores changes the chemical makeup of the universe. In small and sun-like stars, hydrogen fuses into helium for billions of years. In heavier stars, once core hydrogen is used up and conditions allow, helium can fuse into carbon and oxygen. Later, in the most massive cases, fusion can build neon, magnesium, silicon, and finally iron in layered shells. This step-by-step forging of new elements is called stellar nucleosynthesis. Iron is a limit. Fusing iron does not release energy. It costs energy. That means even the largest stars cannot gain power by fusing iron in their cores. To make elements heavier than iron in large amounts, the universe needs extreme events, core collapse supernovae, and mergers of neutron stars provide bursts of neutrons and heat where rapid neutron capture the R process can build gold, platinum, uranium, and many other heavy nuclei. Debris from these events spreads into space and mixes into later generations of clouds. Stars also set structure on larger scales. In a galaxy, the gravity of hundreds of billions of stars helps hold gas in a disk or a spheroid. Massive young stars pour out ultraviolet light and strong winds. They carve bubbles, compress nearby gas, and sometimes trigger fresh rounds of collapse that make new stars. Supernovae drive shock waves that can both clear regions and seed them with heavy elements. In this way, one generation influences the next, and a cycle of birth, feedback, and renewal emerges. Our Sun shows the local version of this influence. Its gravity binds the planets, comets, and small bodies into a system. Its steady light powers weather and photosynthesis and sets climate zones. Its magnetic wind shapes the bubble of space around us, called the heliosphere, which helps shield the inner system from some high-energy particles that move through the galaxy. Ordinary by galactic standards, the Sun is decisive for conditions on Earth. On the largest scales, stars changed the young universe. After the Big Bang, space was filled mostly with hydrogen and helium. The first stars formed a few 100 million years later. Their ultraviolet light reionized the surrounding gas, clearing the early fog and letting light travel far. Their supernovae enriched space with heavier elements, which later helped dust form and made it easier for clouds to cool and collapse. Their gravity helped gather matter into the first galaxies and brightened the early cosmos. The balance of star formation matters. Too few stars, and there is not enough heavy material for complex chemistry. Too many stars forming too fast, and violent feedback tears gas apart or locks it into short-lived giants, leaving little time for stable systems to take hold. Galaxies tend to settle into self-regulated cycles. Gas cools and forms stars. Young stars heat and stir the gas. Some gas leaves. The rest falls back. New stars form again. Over billions of years, this feedback keeps star formation rates within ranges that build long-lived structures. Color, brightness, and spectrum make a simple toolkit to place a star in this story. Blue-white stars are hot and short-lived. Red stars are cool and long-lived. Yellow-white stars like the Sun sit in between. Over time, even a steady star brightens as helium builds in its core. Its output drifts upward at a slow pace measured in percent per billion years. That slow drift has real effects on planets. Early Earth received less energy from the Sun. Geology and atmospheric chemistry had to adjust to keep water stable at the surface. The photon's long walk from core to surface and the quick sprint across space explain why starlight is both old and immediate. The energy that warms a leaf today began as core fusion long ago, while the information in its color and lines tells us the current state of the star that sent it. Light is messenger and power at once. It lets us measure, and it lets worlds run their daily cycles. Stars also imprint order on their neighborhoods through gravity and magnetism. Planetary systems take shape in disks, while stars are still young. The mix of elements in a disk affects what types of planets form and where. Water, ice, and carbon-bearing solids are more common farther from the star, so giant planets often build there, while rocky planets tend to form closer in. Later migration can shuffle those orbits, but the initial pattern comes from temperature and chemistry set by starlight. In regions with many massive stars, feedback can be strong. Intense ultraviolet light can strip electrons from atoms, heating and dispersing gas. Winds can sweep out cavities tens of light years wide. Yet on the rims of those cavities, compressed layers can collapse into new stars. Destruction and creation are linked by the same energy flows. The process can be harsh up close, but produces large-scale order, clusters, associations, and spiral arms rich with both young stars and the gas that will make more. Over time, main sequence stars very slowly change their rotation and activity. Magnetic braking winds dragging on magnetic fields carries away angular momentum, so stars spin more slowly as they age. Slower rotation means fewer strong flares and calmer outer layers. Astronomers can use a star's spin rate and magnetism as a rough clock, a method called gyrochronology, to estimate age alongside color and brightness. Seen together, these threads explain why the main sequence phase deserves such close attention. It is the long, steady heartbeat of the cosmos, quiet, balanced, and deeply generative. During this span, fusion in the core sets the light levels that govern climates, drive photosynthesis, and sustain the slow chemistry that builds surfaces and atmospheres. It is here that many essential elements are forged, and energy is released into space as a steady field of radiation that other worlds inherit. The details differ with mass and composition, but the structure is always the same. Fusion at the center, energy carried outward through layered gas, a controlled release at the surface, and light traveling across the dark to shape the conditions elsewhere. In a universe filled with bursts and endings, this long middle provides the baseline. Against it, supernovae, flares, and collisions appear as momentary departures from calm. Without that baseline of quiet light, complex systems would never have the stability they need to form or endure. The main sequence glow is the background hum of existence, steady enough for order to grow, slow enough for memory to build, bright enough to be traced across time and distance. Too many massive stars gathered in one place can upset that order. Their fierce radiation, fast winds, and explosive deaths clear gas from young galaxies before calmer systems can take shape. Too few, and there is not enough light or heavy matter for planets and chemistry. Over cosmic time, most regions find balance. New stars form as old ones fade. Gas is stirred and cooled, and the mixture allows both change and persistence. You can read the result in ordinary matter, the iron in rails, the silicon in circuits, the oxygen in every breath. Each atom was built in a star, released into space, and used again. To walk the earth is, quite literally, to walk on the remains of ancient suns. Stars do not plan or choose. They follow clear rules. Gravity pulls inward. Heat and pressure from fusion push outward. Matter changes state under temperature and density. From these simple rules come complex results: metals in jewelry, calcium in shells, and the chemistry of life. What looks like purpose is physics at work over long times and large scales. To understand the variety we see in the sky, astronomers sort stars by brightness and temperature using the Hertzsprung-Russell diagram, often called the HR diagram. One axis shows luminosity, the total light a star emits. The other shows surface temperature, which also links to color. When we plot many stars, patterns appear. The largest set lies along a broad band called the main sequence. On that band, stars spend most of their lives turning hydrogen into helium. Where a star lands on the main sequence depends mostly on its mass. High mass means higher temperature and bluer color. Low mass means cooler temperature and redder color. In this sense, mass is a strong guide to a star's path. At the low mass end are red dwarfs. They are small, cool, and faint, and they make up close to 3/4 of all stars. Most are invisible to the naked eye from Earth because they are not very bright, but they are numerous and long-lived. A red dwarf uses fuel slowly and can shine for trillions of years, far longer than the universe has been around so far. Many red dwarfs, formed early in cosmic history, are still burning quietly today. At the high mass end are blue giants and supergiants. They are very hot and very luminous. A single one can outshine the sun by tens of thousands of times. Their mass can be many times the sun's mass, and their sizes can be dozens of times larger. They pay for that power, with short lives measured in a few million years. They end as supernovae that drive shockwaves through their surroundings and seed space with heavy elements. Between these extremes lies a wide range. Orange dwarfs are a bit smaller and cooler than the sun and may live tens of billions of years. Yellow stars like the sun sit near the middle. Subgiants have started to run low on core hydrogen and move off the main sequence. Giants swell to large sizes when fusion shifts from the core to surrounding shells, and when helium begins to fuse in the center. Each type has a zone on the HR diagram and moves along a track as conditions inside change. Color is a simple guide to temperature. Hot stars emit more light at short wavelengths and look blue-white. Cooler stars emit more at long wavelengths and look orange or red. It is the same reason heated metal glows dull red when warm and whitens as it gets hotter. When you notice a red star, you are seeing a cooler surface. When you notice a blue star, you are seeing a hotter surface. Our sun sits in the middle. Not very hot, not very cool. Steady and bright enough to support a wide zone where liquid water can exist on planets. The HR diagram also acts like a record of aging. As a star uses the hydrogen in its core, the core's makeup shifts toward helium. The star must adjust to keep making energy. On the diagram, that shows up as motion off the main sequence into the subgiant and giant regions. Small and medium stars will end as white dwarfs dense, Earth-sized remnants that cool slowly. Very massive stars will collapse and explode, leaving neutron stars or black holes. A single plot can hold all these paths and show how one set of physical rules leads to many outcomes. These differences in stars affect the kinds of planets we find. Red dwarfs often have planets close in because the region warm enough for liquid water is near the star. Some of those planets may keep the same face to the star at all times, with a hot day side and a cold night side. Blue giants are short-lived and turbulent. They light up their regions and can trigger more star birth, but their brief lives leave little time for stable, long-term climates on nearby worlds. Yellow and orange stars tend to provide steady light for long spans, which helps atmospheres and oceans persist. Galaxies show these patterns on large scales, in spiral arms where gas is dense and fresh stars form. You often see bright, blue clusters. In central bulges and halos, where star formation is older and slower, redder, longer-lived stars dominate. The color mix across a galaxy is a map of its history, where gas has been turned into stars quickly, where it has been stirred or stripped, and where it has settled. No two stars are truly alike. Each has a mass, a chemical mix, a spin rate, and a magnetic field that change over time. But the fingerprints are readable. Color gives temperature. Brightness at a known distance gives true luminosity. Spectral lines reveal elements, pressure, and motion. Put these pieces together, and you can tell what a star is, how old it is in broad terms, and how it is likely to evolve. Seen this way, the night sky is not a field of identical points. It is a spread of many kinds of lives playing out at once, on timescales from millions to trillions of years. Some stars will fade so slowly that they outlast the present age of the universe many times over. Others will end soon, by cosmic standards, after a short, intense burn. The Sun sits between these cases. It is a G-type main sequence star with a moderate mass and a moderate surface temperature. That combination gives a long, stable middle life and a broad region where a rocky world can keep liquid water. The mix of stars also shapes the supply of elements. Fusion in stellar cores builds helium, and in massive stars, heavier elements up to iron. The heaviest elements form in extreme events, core collapse supernovae, and neutron star mergers, where intense neutron flux lets nuclei capture neutrons rapidly. Dust and gas enriched by these events cool more easily, form molecules, and build solid grains that become the seeds of planets. Over many cycles, the average composition of star-forming clouds changes, allowing new kinds of planets and chemistry. Back at the scale that matters most to us, there is one star that sets the terms of life on Earth, the Sunday. It is common by galactic standards, yet central in our own system. Astronomers classify it as a G-type main sequence star. Its diameter is about 100 times Earth's. Its mass is a bit more than 330,000 times Earth's. With that mass, its gravity dominates the solar system. Planets, moons, asteroids, and comets orbit, because the Sun's pull sets the shape and pace of their paths. The Sun's light is steady on human timescales. It sets day and night, powers photosynthesis, drives weather, and warms oceans. Its magnetic wind fills a vast bubble, the heliosphere that interacts with charged particles in space and helps shield the inner system. Its spectrum carries fine dark lines that show the presence of elements like hydrogen, helium, calcium, sodium, and iron in its outer layers. Small shifts in those lines reveal surface motion and rotation. Patterns on its surface, granulation, and sunspots come from convection and magnetic fields. Flares and ejections happen, but the baseline output remains close to constant over long spans, which lets Earth keep a stable climate most of the time. The Sun sits in a useful middle. It is neither the hottest nor the largest, and that restraint matters. Very massive hot stars blaze briefly and end fast. Very small, cool stars last far longer, but force any temperate planet to huddle close, inside a narrow habitable zone where strong flares and tidal locking can be common. The Sun offers a broader, steadier lane, a long lifetime, a wide, stable region for orbits, and a spectrum centered in visible light, well matched to water's chemistry and to plant pigments that use that light efficiently. That stability comes from simple, constant work in the core. Hydrogen fuses into helium without pause, turning a small amount of mass into energy every second on the order of 4 million tons, released as light and heat. From about 93 million miles away, that flow reaches Earth at a level that keeps oceans liquid, air in motion, and climates within bounds. This distance falls squarely in the habitable zone, the range around a star where a planet can hold liquid water at its surface. The balance feels natural because it changes very slowly. The Sun does not flicker wildly. It does not flare up and stay bright for years, then fade. Its output varies a little with magnetic cycles, but across human lifetimes, it is almost constant. That constancy spans deep time. When life began in the oceans nearly 4 billion years ago, sunlight drove chemistry there. When dinosaurs walked on land, the same star warmed the ground. When early humans watched the sky, the same star set the pace of days and seasons. This continuity anchors climate, biology, agriculture, and habit. The sun still evolves, but on scales that escape everyday notice. Fusion turns hydrogen into helium in the core, so the core's mix shifts. Helium is denser than hydrogen, and as it builds up, the core contracts and heats a bit to keep the fuse burning. A hotter core means a brighter star. In its youth, the sun radiated roughly 70% of today's power, yet the young Earth had liquid water. This mismatch is the faint young sun paradox. The leading explanations involve greenhouse gases and changes in Earth's reflectivity, more heat trapping, CO2 and methane, different cloud patterns, and darker surfaces likely kept early oceans from freezing. Looking forward, the sun has fuel left for roughly 5 billion years of main sequence life. During that time, it will continue to brighten slowly. Long before it finishes core hydrogen, that extra input will challenge Earth's climate. Over hundreds of millions to a few billion years, higher sunlight could drive stronger water loss and major shifts in the atmosphere. These changes are far beyond human planning horizons, but they are part of the same physics that makes the sun reliable today. When core hydrogen runs low, the structure will change. Gravity will squeeze the depleted core. Temperature will rise. Hydrogen fusion will move to a shell around the core. The outer layers will expand. The surface will cool to a redder color, even as total brightness grows. The sun will become a red giant. In this phase, its radius will swell by tens to hundreds of times. The inner planets will face intense heating. Tidal interactions and drag in the extended atmosphere may draw some inward. Whether Earth gets engulfed or scorched at close range depends on details of mass loss and orbital shifts, but the surface will not remain habitable. Our star is not massive enough to explode as a supernova. Instead, it will shed its outer layers in a series of gentle to moderate outflows, driven by pulsations and radiation pressure on dust. The gas will form a glowing shell called a planetary nebula, a historical term that has nothing to do with planets. The exposed core, no longer making energy by fusion, will be held up by electron degeneracy pressure, a quantum effect that resists further squeeze. That remnant is a white dwarf, about Earth-sized but with roughly half the sun's mass. It will shine from stored heat and cool over billions of years, fading through white and yellow to red and then to infrared. In extreme future times, after unimaginable spans, it will become a dark, cold object, a black dwarf. Even this quiet end spreads useful material. The ejected gas will be rich in carbon, nitrogen, and oxygen formed in later fusion stages, and by surface mixing, dust grains will condense in the flow. Over time, nearby clouds will absorb that matter. New stars will form from the mix, and with them, new disks and planets. The sun's final act will supply ingredients that help future systems build both rocks and organic molecules. The feature that makes the sun stand out for us is stability. Many stars in the galaxy live quickly and die dramatically. Massive blue stars glow intensely for only a few million years. Red dwarfs live far longer but often produce strong flares relative to their size. especially when young, which can stress close-in planets. The Sun's 10 billion-year main sequence offers a wide window, long enough for continents to drift, for biology to explore many paths, and for complex ecosystems to emerge. Human cultures have tracked this steadiness in many ways. Ancient structures align to solstices and equinoxes. Calendars encode the year's solar rhythm. Language reflects sunlight as a marker of time and mood. Science adds detail without removing meaning. We now know the Sun is a sphere of plasma with magnetic fields that rise, twist, and reconnect. We measure spots, flares, and coronal mass ejections, then watch how they affect the near-Earth environment. Through it all, the baseline holds. The average output varies only slightly across decades. The path from core to skin ties daily warmth to slow physics. Energy begins as fusion in a hot, dense center. Photons scatter, are absorbed, and re-emitted countless times on their way out. The time for that energy to reach the surface can be hundreds of thousands of years. Once released as visible light, the trip from Sun to Earth takes about 8 minutes. When you feel sunlight, you feel energy that started as mass in the core long ago, wandered through layers of plasma, and finally crossed space in a straight line. As the Sun ages further on the main sequence, small trends continue. The core gets slightly hotter and smaller. The outer layers adjust. Overall brightness inches upward. Magnetic braking slowly reduces rotation. The wind carries away angular momentum, and the Sun spins a bit more slowly with time. Slower spin often means calmer magnetism. Compared with its youth, the modern Sun likely flares less often and less violently. This gentle drift toward quiet helps surface conditions on planets remain predictable. The late life changes will be gradual, then dramatic. In the subgiant stage, as core hydrogen is exhausted, the radius will expand and surface temperature will decline while luminosity rises. When the core gets hot and dense enough, helium fusion will begin there, turning helium into carbon and oxygen. For a star of the Sun's mass, the start of helium burning arrives through a brief, rapid event called the helium flash in the core, which quickly settles to a new steady burn. Later, when helium runs low, burning shifts to shells again. Each step is a response to the same rule. Gravity presses inward. Fusion, or residual heat, pushes outward. Structure rearranges to find a new balance. Larger stars reach similar waypoints faster and add more layers. Their interiors can look like an onion of burning shells. Hydrogen on the outside, then helium, then carbon, then heavier elements, up to iron in the core. Iron fusion does not release energy, so collapse follows. That path leads to a supernova and a neutron star, or black hole. The Sun will avoid those extremes. Its life story is quieter, but it still links to the wider cycle through the elements it returns to space. Red dwarfs tell a different long story. They mix their interiors efficiently and use fuel slowly. None have lived long enough to show us their end, because the universe is too young. Models say they will become bluer and hotter late in life as their helium builds, then fade over vast times. Their patience sets a limit for how long small, steady lights can shine in the deep future. The Sun's role as the center of our system touches every scale near home. Gravity keeps planets in place. Light drives weather. Magnetic fields shape space around Earth. The heliosphere, inflated by the solar wind, deflects some high-energy particles from the galaxy, changing the radiation environment in which Earth sits. Variations in the solar cycle can nudge the upper atmosphere and affect radio communication and satellites. Space weather forecasting tracks these changes because technology depends on them. Even so, these variations are small compared to the Sun's overall steadiness. Numbers fix the sense of size. The Sun's diameter is about 864,000 miles. Its mass is about 2 × 10^30 kilograms. Surface temperature averages about 5,800 kelvins. The core reaches around 15 million kelvins. Light at Earth's distance arrives with a power of about 1,361 watts per square meter at the top of the atmosphere, a value called the solar constant. Small year-to-year variations cluster within a few tenths of a percent, mostly tied to the 11-year magnetic cycle. When the red giant phase arrives far in the future, mass loss will change the orbits of the remaining bodies. As the Sun sheds material, its gravity weakens, and planetary orbits will drift outward. At the same time, drag in the extended atmosphere, and tides can pull inner bodies inward. The final outcome for each world depends on the exact timing and amounts. Whatever the details, the surface of Earth will not survive as we know it. The record of oceans and rock will end, and the planet's matter will mix back into space. A white dwarf's physics is different from a normal star's. It shines without fusion, cooling slowly by radiating stored heat. Its gravity is strong at close range. A teaspoon of its material would weigh tons on Earth. Without fusion, there is no expansion to offset gravity, but quantum rules set a hard floor on compression, preventing collapse for masses below about 1.4 times the Sun's mass, the Chandrasekhar limit. Our Sun's core will be well below that limit. Through all stages, the key ideas stay simple. Fuel sets power, gravity shapes structure, heat moves outward by radiation and convection, light carries history across space. The Sun fits those rules without excess. It is large enough to make a system and long-lived enough to keep it stable, yet not so large that it burns out fast or ends in violent collapse. That ordinary profile is the reason a small rocky world could keep liquid water long enough for life to arise and adapt. To feel sunlight is to feel a link between nuclear physics and daily life. A star's core work, the random walk of photons, and the vacuum of space combine to warm a leaf, drive a breeze, and set a rhythm for all living things under an open sky. The same processes that will one day turn the Sun into a red giant and a white dwarf are the ones that keep it even and patient today. Aging in stars follows clear steps. The same rules that kept a star steady now push it to change. As hydrogen is used up in the core, helium collects there, and the balance shifts. Gravity tightens its hold. The core contracts and heats. The outer layers respond by expanding, brightening, and cooling at the surface. What looks like instability for the star becomes creation for the galaxy. Each change prepares new elements, carbon, oxygen, and others that will later mix into space. The end of a steady phase is also the start of raw material for planets and for life. The night sky holds many of these stages at once. Some stars stay in their long calm. Others have begun to move off that path, their light shaped by deeper changes. Stability, it turns out, is a phase. It lasts a long time, but it does not last forever. The steady shine that set the pace for nearby worlds will, in time, drift into a warmer, larger, redder state. The melancholy part is that a known light is changing. The useful part is that change delivers new matter to the next generation of systems. The turning point comes when core hydrogen is no longer enough to hold balance. Gravity squeezes the helium-rich center. The temperature climbs. Hydrogen fusion shifts from the core to a shell around the core, and the outer layers expand. The star becomes a red giant. The scale is hard to picture. A star that once fit within a modest volume can grow hundreds of times larger in radius. For the Sun, that means an inflated surface reaching to the orbits of Mercury and Venus, and possibly beyond. Even if Earth were not engulfed, the heat would sterilize its surface. From far away, the growth is smooth. Up close, the physics is firm. A hot, contracting core pushes energy outward. Thin outer layers puff out and cool to a reddish-orange glow. As the core keeps heating, helium nuclei begin to fuse. 3 helium nuclei, alpha particles, combine to make carbon. Sometimes, a 4th helium joins to make oxygen. This triple alpha process needs about 100 million kelvins in the center. In stars like the Sun, the core at this stage is degenerate. Pressure arises mostly from quantum effects of packed electrons, not from temperature. In a degenerate gas, pressure does not expand much when heated. When helium fusion starts, the lack of expansion allows temperature to jump quickly, raising the fusion rate in a brief runaway called the helium flash. Despite the name, the star does not explode. The flash lifts degeneracy. The core expands slightly, and the star settles into a new balance with helium burning in the center and a calmer surface. While the surface looks cool, the total light output is large because the surface area is huge. A red giant can be thousands of times more luminous than it was on the main sequence. Its extended atmosphere is thin and loosely bound. Pulsations and radiation pressure on dust grains in the outer layers can drive a strong wind. Gas and dust stream away, forming shells and arcs that drift into space. The star becomes a source of carbon-rich and oxygen-rich material that later condenses into grains in cold clouds. This outflow is destructive for nearby worlds, but constructive for the galaxy. Inside, the structure becomes layered. Hydrogen fuses in a shell outside the core. Helium fuses in the core. In more massive stars, the pattern adds more shells. After helium, carbon can fuse into neon, sodium, and magnesium if the core reaches the required temperature. Later, oxygen can fuse into silicon and sulfur. Finally, silicon can fuse into iron group elements. Each step needs higher heat and runs faster. Hydrogen burning can last billions of years. Carbon burning, thousands of years. Oxygen burning, months. Silicon burning, days. The timeline compresses as the center grows hotter and denser. The onion-like layers of a very massive star are distinct. At the center sits an iron core. Around it are shells of silicon burning, then oxygen, neon, carbon, helium, and hydrogen in order. Iron marks a hard stop for fusion power. Fusing iron does not release energy. When the iron core grows beyond what pressure can support, it collapses. That rapid collapse and rebound power a core collapse supernova, which hurls the outer layers into space and leaves a neutron star or a black hole. The supernova's shockwave and the flood of particles forge many elements heavier than iron and carry them outward. Nearby clouds get enriched. Future stars and planets inherit the mix. Stars about the size of the Sun live a quieter end. After helium is used up, the core contracts again. Hydrogen and helium burn in shells for a time, and the outer layers grow unstable and loosely bound. The steady wind strengthens. The star sheds its envelope, exposing a hot core. Ultraviolet light from that hot core makes the drifting gas glow. We call the glowing shell a planetary nebula, a name from early telescope days when these small round shapes looked like planetary disks. The core becomes a white dwarf, Earth-sized, dense, and hot at first, then cools slowly for billions of years, shining without fusion. Its gravity is held in check by electron degeneracy pressure, safe below the Chandrasekhar mass limit. Red giants in the sky show us these futures in real time. Betelgeuse in Orion and Antares in Scorpius are familiar examples. Place Betelgeuse at the center of our system, and its surface would reach beyond Mars. Their light is red because their swollen surfaces are cooler, not because the interior is quiet. Inside, deep layers run hot, and the outer atmosphere is flowing outward in a wind loaded with dust grains. Observations at infrared and radio wavelengths map these winds and show arcs and clumps blown off over time. The expansion and wind are not smooth. Many aging stars pulsate. Their outer layers rise and fall on set rhythms. In red giants and red supergiants, these pulses can help lift gas outward where dust can form. Once dust forms, radiation pressure pushes on it, and the dust drags gas along. Over time, this mass loss can remove a significant fraction of the star's mass. In more massive stars, the wind, and later the supernova, set how much material is returned and how much collapses inward to form a compact remnant. The shell-burning structure also explains why brightness can vary. When fusion in a shell strengthens, energy output rises, the outer layers expand, surface temperature drops a bit, often making the star redder, but more luminous overall. When fusion in that shell wanes, the layers can settle. In some stars, helium shell flashes occur, brief episodes when the helium-burning shell becomes unstable and dumps extra energy outward. These thermal pulses can drive strong mass loss and shape the nebula that forms later. For stars somewhat heavier than the Sun, but still below the supernova range, the core after helium burning can reach carbon ignition. Carbon burning happens in short surges and creates neon, sodium, and magnesium. If the mass is not high enough to continue to oxygen burning, neutrino cooling and mass loss can halt the advance, and the star may still end as an oxygen neon magnesium white dwarf. For higher masses, the progression continues all the way to iron. The general rule stays the same. Higher mass drives to higher core temperatures, more layers, faster late stages, and more dramatic ends. Even the red giant's cool surface tells a useful story. A lower surface temperature shifts the star's spectrum toward longer wavelengths. Molecules can form in the outer atmosphere, like titanium oxide in cool giants, producing absorption bands that mark temperature and chemistry. Spectra also reveal outflow speeds and composition of the wind. In the circumstellar envelope, dust species silicates if oxygen-rich, carbon dust if carbon-rich, emit at infrared wavelengths. These signatures let us trace how different stars seed space with different kinds of grains. The life of nearby worlds during this phase depends on distance and timing. Planets, once in comfortable orbits, may face moving boundaries. As the star loses mass, its gravity weakens and orbits can expand. At the same time, drag in the extended atmosphere, and tides can draw close planets inward. In dense inner regions, moons and small bodies can be stripped farther out. Cold surfaces can warm enough to release trapped gases or melt ices. A single system can go from quiet order to reshuffling and loss as the central star evolves. The timescales remain large, even now. For a sun-like star, the red giant phase can last on the order of 1 billion years, including stages of helium core burning and later shell burning. That is long enough for the star to shed a sizable envelope, for a glowing nebula to form, and for that gas to drift away and blend into surrounding space. The white dwarf that remains will cool for longer than complex life has existed on Earth so far. The path for massive stars runs faster. After the main sequence, they pass through supergiant stages blue, yellow, or red. While adding shells of fusion, their winds can be extreme, peeling off outer layers and shaping bubbles tens of light years across. When collapse comes, the supernova releases more energy in seconds than the star radiated during its entire life. In that brief event, shock heating and neutron capture build many heavy nuclei. The shock and the later pulsar wind, if a neutron star forms, stir and energize the local medium, often driving fresh collapse in nearby clouds. Across all these cases, the theme is balance responded to and revised. Gravity presses inward. Fusion or stored heat pushes outward. When fuel changes, the balance shifts. The star adjusts by moving energy generation to new layers, changing size, and often shedding mass. The outer outcome can be gentle in appearance, a red glow, a steady wind, or sharp and sudden, a supernova flash. Either way, the products are the same kind of things we hold and breathe. Carbon for life's chemistry, oxygen for water and air, silicon for rocks, iron for cores and tools, and trace heavy elements for technology and biology. Seen on a diagram that plots temperature against brightness, these steps follow clear paths. A star leaves the main sequence, climbs the red giant branch, settles on a horizontal branch or red clump when helium burns in the core, and then moves to the asymptotic giant branch when shell burning dominates again. Pulses and winds mark the late stages, then the track rolls down as the white dwarf cools. Massive stars cross from the main sequence to supergiants, wander in temperature as shells add up, and end at the point where the diagram cannot follow further because the star has become a compact remnant. The inevitability is not bleak, it is productive. Each contraction, each new shell, each outflow is part of how the galaxy replaces raw hydrogen with a working mix of elements. Clouds enriched by earlier stars cool more easily and form stars more efficiently. Disks around new stars carry more solids, which helps planets form. The rhythm is patient and cumulative. The instability of an aging star is the method by which later stability on planets and in ecosystems becomes possible. When we identify Betelgeuse or Antares by their red light, we are reading this script at a glance. Their color says, cool surface, immense size. Their brightness says, large area, high output. Their subtle changes hint at deep layers shifting. They are not special exceptions. They are standard outcomes for certain masses. The Sun will follow its own milder version: expansion, helium burning, wind, nebula, white dwarf. The matter it sends back will become part of other clouds. Somewhere, later, those clouds will fall together. Light will start in a new core, and the cycle will continue under the same rules. The layered interiors of aging stars stay hidden, but their effects are measurable. As fuels switch on and off in shells, a star swells and contracts, brightens and dims. Some show rhythmic pulsations, like a slow breathing. Dense winds strip the outer atmosphere and carry dust into space. By tracking changes in brightness and color, and by reading spectral lines for temperature, motion, and chemistry, astronomers reconstruct what is happening far below the surface. The sky is silent, but the data speak. The engine behind the layers follows a simple rule. When one fuel runs low, the core contracts. Contraction raises pressure and temperature. Higher temperature unlocks the next fusion step. The cost is speed. Each later stage releases less energy per unit mass and runs faster. Hydrogen burning can last billions of years. Helium lasts hundreds of millions. Carbon, thousands. Oxygen, months. Silicon, days. A patient star becomes a hurried one, sprinting through the final fuels. This rush leaves a lasting imprint. Every element heavier than helium comes from these inner workshops. Carbon in pencils and cells, oxygen in air and oceans, magnesium in chlorophyll, silicon in sand and circuits, calcium in bone, iron in blood, and planet cores each was forged in stars. Without layered fusion, the universe would remain a thin mix of hydrogen and helium, poor in chemistry and poor in options. On the outside, a late-stage star looks grand and fragile at once. The surface area can grow so much that total light rises to thousands or tens of thousands of solar luminosities, yet the outer gas is thin and easily lifted by pulsations and radiation pressure. The whole structure rests on temporary supports, shells that will burn out. The clock is the order of layers, hydrogen around, helium around carbon, and so on each shell, marking time until the next step begins. How the story ends depends on mass. Stars like the Sun and smaller cannot push to the hottest reactions. After helium is used, they cannot fuse carbon in a stable core. Their outer layers drift away in winds, and the exposed core becomes a white dwarf. Massive stars, with higher central temperatures and pressures, continue through carbon, neon, oxygen, and silicon. When the core reaches iron, energy from fusion stops paying the bill. The layered onion collapses and sets off a supernova. Before that last act, the interior is a precise stack of burning shells, a natural reactor with nested stages. Think of the layers as a clock face you cannot open, read only by the shadows it casts. Hydrogen gives way to helium. Helium builds carbon. Carbon makes new paths for neon and magnesium. Oxygen builds silicon and sulfur. Silicon feeds iron. Each ring of this clock ticks faster than the last. The inevitability is not bleak, it is productive. It is how the periodic table gets filled and how worlds earn their materials. Most stars, however, end without an explosion. Their end is the white dwarf. The steps are clean. Fusion stops in the core. Gravity squeezes. Under extreme compression, electrons resist being packed into the same quantum states. That resistance is electron degeneracy pressure. It is not heat. It is a quantum rule that says no two identical fermions may share a state. Degeneracy halts collapse at a size comparable to Earth, with a mass comparable to the Sunday. A teaspoon of white dwarf matter would weigh tons on Earth. A new white dwarf is hot and bright, glowing at tens of thousands of degrees. There is no fusion to replace the heat. It cools by radiating, slowly dimming from white to yellow to red to infrared. The cooling takes longer than the current age of the universe, which is why none have yet become fully dark black dwarfs. Every white dwarf we detect still glows, however faintly, a quiet ember from an earlier star. Planets around such a remnant would see a deep twilight. A point-like star would flood little heat. Oceans would freeze. Air could collapse to the ground. The system would become a cold archive of earlier weather and geology, yet the remnant itself remains informative. Spectra of white dwarfs tell us about their composition. Most are carbon-oxygen cores, some are helium, and some, from slightly higher mass parents, carry traces of oxygen-neon-magnesium. Cooling rates act like clocks. Together with masses and temperatures, they let astronomers date stellar populations. There is a hard mass limit for white dwarfs. If the core that tries to become a white dwarf exceeds about 1.4 times the Sun's mass, the Chandrasekhar limit electron degeneracy pressure cannot support it. Above that, a different fate waits. Further collapse toward a neutron star or a black hole, or, in special cases, a thermonuclear explosion. That limit draws a clean line between quiet endings and violent ones. Our Sun's path fits the quiet case. After a red giant phase and a period of strong winds, it will leave behind a carbon-oxygen white dwarf, roughly half the Sun's mass. Around it, a glowing shell, a planetary nebula, will briefly light the gas pushed off during the final pulses. The core will cool for billions of years. Red dwarfs, the most common stars, will take much longer to reach this stage because they burn fuel so slowly. None has yet died. In the remote future, long after larger stars have vanished, red dwarfs will still burn. When they finally fade, they too will leave white dwarfs behind. White dwarfs do more than fade. In some binaries, a white dwarf can pull gas from a companion. If the inflow is steady, the white dwarf grows. Near the Chandrasekhar limit, conditions trigger a runaway thermonuclear reaction through the carbon-oxygen core. The entire star ignites in a type Ia supernova. These events are bright, consistent in peak luminosity, and visible across vast distances. They seed space with iron group elements and serve as reliable yardsticks for mapping the scale of the universe. Many white dwarfs never reach this point. They simply cool in silence. But the potential remains a quiet ember with a rare path to sudden brilliance. Even without binaries, the winds from aging low and intermediate mass stars are important. They create carbon dust in carbon-rich stars and silicate dust in oxygen-rich stars. These grains flow into space, mix into cold clouds, and later become the seeds for planets. Observations at infrared wavelengths reveal these dust signatures and the speed and composition of the outflow, linking late stellar life to the chemistry of new systems. At the other extreme, massive stars add layers and speed. Their post-main sequence stages pass quickly. Their winds can strip their envelopes before collapse, revealing hot blue surfaces again and producing Wolf-Rayet stars with strong, broad emission lines. When fusion in the core builds an iron core, collapse becomes unavoidable. Iron is the end of energy gain from fusion. Adding heat to an iron core does not make more pressure. Instead, electrons are captured by protons. Neutrinos rush out and support collapses. The core falls in a fraction of a second, rebounds, and a supernova shock is launched. Some shocks stall and are revived by neutrino heating and turbulent flow. Some push straight through. In either case, the outer layers are blasted away. This path produces compact remnants. If the remaining core is between roughly 1 and 2 solar masses after the ejected layers are gone, it can be held up by neutron degeneracy pressure as a neutron star, city-sized, incredibly dense, with magnetic fields and rotation, that can make it a pulsing radio source. If the core is more massive, gravity wins and a black hole forms, a region where escape speed exceeds the speed of light. Which object forms depends on mass, rotation, metallicity, and how much material fallback adds after the explosion. For a while before collapse, a very massive star looks like a cross-section in action. From the center outward, iron core, silicon burning shell, oxygen burning shell, neon, carbon, helium, hydrogen. Each shell burns at a different rate. The stellar surface may show irregularities and episodic outbursts as deep changes couple to the outer atmosphere. Some stars eject thick shells just years before collapse, leaving dense surroundings that light up when the supernova shock runs into them. Light curves and spectra taken in the first days after explosion preserve these conditions, letting astronomers read the last years of a star's life. The same measurements that decode a protostar's birth decode a giant's decline. Brightness over time, a light curve shows pulsations and outbursts. Spectra show temperature, chemical fingerprints, and velocities through Doppler shifts. Infrared excess marks dust. Radio maps show molecular outflows. X-rays pick up hot shocks. Put together, they draw a clear picture. The interior layers change, the outer atmosphere responds, and the star sheds what it cannot hold. In low and intermediate mass stars, helium ignition can begin abruptly if the core is degenerate, a helium flash that lifts degeneracy and settles the star into stable helium burning. Later, when core helium is gone, hydrogen and helium burn in shells. The star moves to the asymptotic giant branch, where thermal pulses, brief helium shell runaways, push the outer layers and drive heavy mass loss. Each pulse builds the surrounding nebula that will soon glow when the core is laid bare. In higher masses, each new fuel demands hotter temperatures and runs for shorter spans. Carbon burning builds neon, sodium, and magnesium. Oxygen burning builds silicon and sulfur. Silicon burning assembles iron group nuclei in a rapid network of reactions. At the iron stage, the energy ledger turns against the star. Without energy from fusion, gravity takes over. Neutrino emission saps heat. The core's pressure support fails. When the star can fuse no more, its balance collapses. Gravity finally takes control when fusion can no longer pay the cost. An iron core cannot add pressure by fusing further, so support fails. In a fraction of a second, the core collapses. Electrons are forced into protons, making neutrons and a flood of neutrinos. The infalling outer layers hit the stiffening core and a shock forms. With help from neutrino heating and turbulent motion, that shock can break free. The result is a core collapse supernova, one of the most energetic events in the universe. Calling it an explosion understates the scale. The star releases more energy in moments than the sun will emit in 10 billion years. For weeks to months, the light from a single event can rival that of an entire galaxy. People in the past noticed such lights even without telescopes. A bright guest star, recorded in 1054, formed what we now call the Crab Nebula, still expanding and glowing as the shock heats gas and magnetic fields guide charged particles. The physics inside the blast is harsh, but clear. Temperatures rise to billions of degrees. Rapid neutron capture and R process can build very heavy nuclei that normal fusion cannot make. Gold, platinum, and many other heavy elements are formed or dispersed here. When the outer layers are ejected, those atoms mix into space. Later, they will cool, join dust and gas, and become part of new stars and planets. Without supernovae, the universe would be poor in the materials needed for rock, water chemistry, and biology. A supernova reshapes its neighborhood. The expanding shock compresses some clouds and clears others. Compressed regions can collapse into new stellar nurseries. Cleared bubbles can grow for dozens of light years. Remnants shine for thousands of years at many wavelengths. Visible light from shocked filaments, infrared from warm dust, radio from electrons spiraling in magnetic fields, and X-rays from very hot gas. Each band reveals a part of the flow and the makeup of the debris. At the center, the fate depends on core mass. If the leftover core is below a limit, neutron degeneracy pressure stops the collapse and a neutron star forms. If the mass is higher, even neutrons cannot hold back gravity and a black hole forms. Either remnant changes the region around it. A neutron star can power a wind of particles and radiation. A black hole can feed on nearby matter and light it up as it falls inward. Supernovae are not uncommon on galactic scales, though dust often hides them from our eyes. In a large spiral like the Milky Way, one event every century or so is expected on average. Other galaxies show them often in modern surveys. From Earth, the risk is low. A core collapse supernova would need to occur within about a few tens of light years to pose severe danger. No known candidates lie that close. For us, supernovae are distant laboratories and engines of renewal. The link between destruction and creation is direct. A massive star spends a few million years making light and building elements in layers. In its final second, it gives up that structure and sends those elements outward. Shockwaves stir gas. Dust grains grow in the cooling flow. Radiation clears paths and marks the edges of new shells. Star formation picks up again, where gas is compressed. This cycle keeps galaxies active and prevents their gas from sitting unused for ages. When the core stops just short of making a black hole, the object left behind is a neutron star. It is only about 20 kilometers across, but it holds more mass than the Sunday's surface. Gravity is enormous. Drop something from a meter above, and it would hit the surface at a significant fraction of light speed if nothing were in the way. Magnetic fields can reach trillions of times Earth's field. Matter is arranged in states that do not occur elsewhere. A thin, solid crust of exotic nuclei on top, superfluid neutrons deeper in, and perhaps more exotic phases toward the center. Neutron stars spin. As the core of the dying star shrinks, rotation speeds up, like a skater pulling in their arms. Some new neutron stars rotate many times per second, some much faster. Their magnetic poles may not line up with their spin axis. Beams of radiation emerge from the poles. As the star rotates, the beams sweep across space. If one crosses Earth, we detect regular pulses at radio, X-ray, or gamma-ray wavelengths. Such objects are called pulsars. Their pulses can be timed with great precision, down to microseconds for the fastest. This regularity makes them useful tools. Arrays of millisecond pulsars spread across the sky act like a giant detector for slow ripples in space-time. Spacecraft can also use bright pulsars as natural beacons, comparing pulse arrival times to locate themselves far from Earth. Neutron stars are not quiet in every setting. In a binary system, a neutron star can pull gas from a companion. The gas forms a hot disk and heats to X-ray temperatures as it spirals inward. Some systems launch jets. The flow can switch between calm and burst-like states as magnetic fields and pressure change. If two neutron stars orbit each other, they slowly lose energy to gravitational waves and spiral together. In the last second, tides tear matter and fields apart. A bright flash rises, and a kilonova appears, light powered by the rapid formation of heavy elements in the ejected neutron-rich material. The merger sends a sharp signal of gravitational waves that instruments on Earth can detect, and a fading glow across the spectrum that telescopes can follow. This is one path by which the universe makes a large share of its heaviest elements. A black hole forms when the collapsing core exceeds the mass that neutron pressure can support. The event horizon marks a boundary from which not even light can escape. Outside, an accretion disk can light up as gas falls inward, and jets can carry energy far out. If the black hole remains in a binary, it can produce bright X-ray outbursts when it feeds. If it sits alone in a supernova remnant, it may be quiet, marked only by motions of nearby gas and stars. Observations of supernovae tie these pieces together. The light curve, the brightness over time, shows how much nickel 5-6 was made and how energy leaks from the expanding debris. Early spectra reveal the outer layers. Later spectra show deeper layers as the ejecta thin. Narrow lines can betray dense shells that the star shed shortly before it died. Fast, blue light at the start can point to shock heating at the surface. A late bump can signal interaction between the expanding shock and a thick wind from the star's late life. By comparing models with data, astronomers infer the star's mass, wind strength, and even its last few years of instability. Not all bright endings come from core collapse. Some supernovae start with white dwarfs. In a close binary, a white dwarf can gain mass from a partner. If it reaches a critical mass near the Chandrasekhar limit, or if two white dwarfs merge and reach the right conditions, carbon fusion can ignite through the star and unbind it. These type Ia supernovae are bright and follow patterns that let us use them as standard candles. By measuring their brightness and redshift, astronomers map distances and the expansion of the universe. This method helped reveal that cosmic expansion is accelerating. Each kind of supernova enriches space in a different way. Core collapse explosions tend to spread oxygen, magnesium, and other elements common in massive star layers. Type Ia events are rich in iron group elements. Over time, both types mix into galaxies and set the chemical baseline for new generations. A planet's rocks and a cell's molecules record this mix. Silicates in crusts, iron in cores, carbon in organics, calcium in shells and bones. The Crab Nebula shows what a remnant can be. At its center sits a neutron star, a pulsar spinning about 30 times per second. Its wind powers a bubble of high-energy particles and magnetic fields. Filaments rich in oxygen, nitrogen, and sulfur line the edges. The whole structure expands at about 1,000 kilometers per second. In other remnants, shock fronts draw long arcs. Where the shock hits a dense clump, it slows and brightens. Where it runs through thin gas, it races ahead and fades. Each remnant is a map of the medium into which it expands and of the star that made it. The neutrino burst from a nearby core collapse carries messages from the center. Neutrinos interact weakly, so they escape the core in seconds, long before light can. Detectors have captured such bursts from events in the Milky Way's neighbors. In the future, a core collapse event in our galaxy would first light up neutrino monitors, then show a rising light curve at visible wavelengths hours later. Combining the two will give a sharp test of models of how the shock revives and how the explosion proceeds. Neutron stars also glitch. Their spin, measured to many decimals, sometimes jumps slightly faster. The likely cause is a sudden shift in the superfluid interior, exchanging angular momentum with the crust. These small steps reveal the state of matter beneath the surface. Magnetic fields can twist and snap as well. In magnetars, neutron stars with especially strong fields, such shifts can release short, bright bursts of high-energy light. Massive star endings leave marks on larger scales too. The chemical pattern of a galaxy, how heavy element abundance changes with distance from the center, depends in part on where supernovae occur and how their products mix. The thickness and temperature of the gas disk depend on the energy and momentum injected by explosions. Spiral arms can be traced by chains of bubbles and shells. Even the rate at which new stars form feeds back on itself through this energy budget. From star birth to star death, the same ideas repeat. Gravity gathers gas, fusion lights the core and pushes back, layers add up. When the fuel that adds pressure runs out, gravity wins again, and the structure changes or ends. The last step for a massive star is fast, but it is connected to everything that came before. The onion-like interior sets the seeds of the spectrum we measure after the blast. The winds before death set the stage for the shock after. The core's mass sets the remnant. The debris sets the chemistry of what forms later. Pulsars extend the useful life of a dead core. Their regular timing makes them tools for detecting slow space-time waves and for building navigation methods far from Earth. Their beams, though strong, are narrow, so most never sweep across us. The handful that do provide a clean sample, as they spin down, they convert rotational energy into light and particles, feeding their nebulae and slowly quieting. Some pick up speed again by drawing in gas from a partner, becoming recycled millisecond pulsars. Some pairings end in merger, and the short gravitational wave chirp and kilonova flash tell us when and where that happened. Across these paths, numbers help keep the scale straight. A neutron star's radius is about 10 to 15 kilometers. Surface gravity is about 100 billion times Earth's. Magnetic fields can reach 1 trillion Gauss. Pulsar periods range from seconds down to a millisecond. Supernova ejecta expand at thousands to tens of thousands of kilometers per second. Remnants can span tens of light years after a few tens of thousands of years. These values sound large, but they come directly from simple mass, size, and energy balances. The chain of events from core collapse to remnant fits a plain outline. Fusion halts at iron. The core collapses and stiffens. A shock forms and is powered by neutrinos and turbulent flow. The envelope is ejected. A neutron star, or black hole, remains. The shock sweeps up gas, making a remnant that shines across the spectrum. Heavy elements mix into clouds. New stars form. Some of those stars will be massive and start the cycle again. Others will be calm and long-lived. The process turns a simple early universe into a chemically rich one, piece by piece and event by event. Some endings are loud. Supernovae light up a galaxy. Kilonovae make heavy metals in a flash. Pulsars tick with uncanny regularity. Another ending is quiet and final, the birth of a black hole. It begins in a very massive star, far heavier than the Sunday as fuel is spent. The core builds heavier elements step by step until iron forms. Iron is the stop sign. Fusing it does not release energy. With no power source left, gravity takes over. The iron core collapses in less than a second. If the mass is high enough, not even the pressure that holds up a neutron star can resist. The core is crushed past the limits of ordinary matter. A singularity forms, wrapped by an event horizon, the boundary from which nothing can return. A black hole comes into being. From outside, the change is hard to see. The collapse is violent, yet the black hole itself emits no light. The event horizon is not a surface, it is a threshold. Cross it, and escape is impossible. Light from matter falling in is stretched and dimmed until it fades. Time near the horizon runs slow compared with the outside world. To a distant observer, an object seems to hover and redden as it approaches the edge. The rules we use for normal matter break down inside. Our best equations point to extremes where space-time is curved beyond our current understanding. Black holes come in sizes. Some are a few to tens of solar masses, made by single stars that collapsed. Others sit in galaxy centers with millions to billions of solar masses. Their exact origin likely involves early seeds that grew by merging and steady feeding, but the details remain an active field of study. Large or small, they share the same core idea. Gravity rules completely within the horizon. They are not cosmic vacuum cleaners. A planet at a safe distance would orbit a black hole the same way it would orbit any object of equal mass. The difference shows up when matter comes close. Gas spirals inward in a disk. Friction and magnetic fields heat the disk to high temperatures. The inner regions glow in X-rays and gamma rays. Some systems launch jets from the poles that reach across light years. Ironically, regions around black holes can be among the brightest places in the universe, even though the hole itself is dark. A stellar mass black hole is an ending for a star and a beginning for a new, long-lived object. Left alone, it persists. In theory, a black hole can lose mass by Hawking radiation. Quantum effects near the horizon produce a slow leak of energy. For stellar mass holes, the evaporation time is far longer than the age of the universe, so they are effectively permanent on any human or planetary timescale. We find them by their influence. A star orbits something unseen. A bright X-ray source flickers where no normal star is visible. Orbits of nearby stars curve around a point with great mass and no light. Supermassive black holes sculpt galaxies. When gas falls toward the center, the inflow can light up as an active galactic nucleus. Radiation and jets can blow out gas, heat it, or stir it. This feedback can slow star formation in the core and set a balance between growth and rest. Without such regulation, some galaxies might form stars too quickly and run out of gas. With it, they stay active over longer spans. Even quiet stellar black holes add texture to a galaxy's mass and help shape the long-term dynamics of star clusters where they reside. The path to a black hole is simple in outline. Fuel runs out, iron forms, collapse begins. If the core is heavy enough, no known pressure can stop the fall. An event horizon forms. The star's surface and outer layers may be thrown off in the explosion or fall back later. Either way, the core's fate is sealed. The result is invisible to direct view but leaves a clear signature through gravity and through light from matter still on the outside. This outcome stands next to another, more personal story. What stars make and what we are made of. After the Big Bang, the universe held mostly hydrogen and helium, with tiny traces of lithium. That mix is not enough for complex chemistry. Stars built the rest. In their cores, hydrogen fused into helium. As stars aged, helium fused into carbon and oxygen. Massive stars went further, making neon, magnesium, silicon, sulfur, and up to iron in layered shells. Elements heavier than iron needed more extreme settings, core collapse supernovae, and neutron star mergers, where free neutrons are abundant and nuclei can capture them quickly to build gold, platinum, uranium, and more. Each element in your body tells a part of that story. Iron in hemoglobin binds oxygen for transport in blood. Iron in that form did not come from steady fusion. It formed in the last moments of massive stars or in the radioactive chains set off by explosions, then was hurled into space. Carbon is the backbone of organic molecules. It forms in a delicate step from helium when a specific energy state, the carbon 1,2 resonance, lets 3 helium nuclei combine efficiently. Without that resonance, carbon would be scarce, and life as we know it would be unlikely. Oxygen, vital for water and respiration, comes from helium fusion in massive stars and now fills air, oceans, and cells. Silicon condenses into minerals and later into microchips. Calcium builds bones and teeth. Trace elements like copper, zinc, and iodine also trace back to stellar cores and explosive events. The distribution of these elements is a cycle. A star forms from gas, enriched by earlier stars, lives for millions to billions of years, then returns matter to space through winds or explosions. Clouds with this enriched gas cool more easily because molecules and dust radiate heat effectively. They collapse faster and form more stars and planets. Each cycle adds to the inventory for chemistry and geology. Over billions of years, a galaxy grows more diverse in what it can build. Hold a ring of gold and you hold a record of a rare event, likely the merger of 2 neutron stars or a special kind of supernova. The time and place of that event are unknown, but its results are in your hand. Look at a silicon chip and you see a path that runs from a cooling supernova shell to sand, to a refined crystal, to logic etched by light. Breathe in oxygen and you draw on a chain that runs from fusion in massive stars to air kept stable by plant life under sunlight. Ancient people made myths because the sky felt close and powerful. Their stories were poetry. The measured story is no less deep. Those stars were not only guides and symbols, they were factories and archives. The sun today still fuses hydrogen into helium. In a distant future, it will swell, shed its outer layers, and send carbon and oxygen back into space. That material will mix and join new clouds. Future stars will form. Some will have planets with water and air. Some of those planets may host life. In that sense, the sun is part of a larger, long pattern. Cosmic recycling is a simple name for it, but the process is more than reuse. Matter changes role. It leaves a star as gas and dust, becomes rock and ice in a disk, turns into a crust, an ocean, or an atmosphere, and sometimes becomes part of a living cell. Carbon that once drifted in a giant's wind now sits in DNA. Oxygen from a supernova now moves in and out of lungs. Calcium from a dying star now supports a step on a path. This is not metaphor. It is the direct path of atoms through time. Black holes fit into this cycle too. They end stars, shape flows, and set boundaries. They anchor orbits and power bright jets that can compress or clear gas on large scales. They are extreme, yet they connect to ordinary things through gravity, which acts the same on an apple, a planet, or a galaxy. The same law that keeps your feet on the ground is the law that bends light around a black hole. We learn of black holes and stellar debris by measuring. Stars orbiting an unseen mass trace curves that give us the mass inside. X-ray flares from a point reveal a hot disk. Radio jets point back to compact engines. Ripples in space-time gravitational waves arrive from merging black holes and neutron stars, carrying a clean signature that tells us the masses and spins of the objects involved. Spectra of gas show how fast it moves and what it is made of. Each tool adds a line to the picture. A black hole that feeds slowly may sit quiet for long periods. A change in a companion's wind or orbit can turn it bright. A supermassive black hole can be silent for ages, then flare when a cloud or star wanders too close and is torn apart in a tidal disruption event. Debris forms a disk, heats, and glows as it falls in. The light fades over months. These brief windows show us how gravity and motion convert mass into light without fusion. None of these paths are single events. A massive star may blow strong winds before it dies, shaping the space around it. The explosion then runs into that wind, and the light curve shows it. A neutron star can spin down, glitch, and flare as its crust shifts and its field twists. Two black holes can orbit for eons before merging in seconds. Each step is slow, then fast, then slow again, set by the same physics, but playing out across many scales. The universe did not begin rich in choices. It began simple. Stars made it complex. They provided heat and light for climates, pressure for winds, and elements for rocks and life. Their endings, white dwarfs, neutron stars, black holes, carry forward the results of that work. Some ends are bright, some end in a hush. The quiet ones, like black holes, are not empty endings. They are steady presences that keep time in gravity's language, while matter elsewhere tries new arrangements. Stand outside on a clear night. You will not see black holes. You will see bright points of ongoing fusion and the faint glow of gas lit by stars. Hidden among those patterns are places where a star ended and left behind curved space-time. Hidden in your body are atoms that tell of hot cores and violent blasts. The same laws that made a horizon no light can cross also made the iron in blood and the carbon in thought. The link is not poetic license. It is the line from fusion to dust, to planet, to person, with gravity guiding each turn. As stars burn and die, the mix of elements changes. As the mix changes, new kinds of worlds and chemistries become possible. As those worlds form, some of them become places where light and water and time work together. The record of that process is in spectra, in rocks, and in the quiet pull of masses we cannot see. The path from a hot core to a black hole is one branch. The path from a hot core to oxygen in air is another. Both began in the same simple gas, both follow the same rules, and both continue as long as there is matter to gather and time to act. Continuity runs through this story. Stars end, but they do not vanish. Their matter stays in the game, reheated, mixed, and used again. Life is part of that flow, not apart from it. To breathe, walk, and think is to join a chain that began in clouds, passed through stars, and returned to clouds. You are not a visitor in the universe. You are a piece of it, built from its common stock, borrowing atoms that have already lived many lives. This view is grounding. It turns the night sky from a distant show into a record of family history. Oxygen in a breath once sat in a star's core. Iron in blood once rode inside superheated gas in an ancient blast. Calcium in bone once drifted as dust in a red giant's wind. These are plain facts from chemistry and physics. They do not shrink wonder, they give it a place to stand. Because the legacy of stars is more than light. It is structure and substance. Mountains rise because rocks exist. Rocks exist because heavy elements exist. Heavy elements exist because stars made them and shared them. Rivers flow because water forms. Water forms because hydrogen met oxygen, forged in stars. Forests grow because sunlight powers chemistry in leaves. That light began as mass in the sun's core. The steady work of stars, spread over billions of years, built a world where thinking creatures can ask where they come from. Across cultures, people filled the sky with meaning long before telescopes, temples, calendars, and stories linked human life to the stars' regular motion. That layer of meaning remains, even as science explains the physics. It turns out the connection is even closer than myth guessed. Not only are stars guides and markers, they are also the source of the atoms that make guides and markers possible. The physical cycle can be followed in the sky. Late in life, small and medium stars puff up and lose their outer layers. They build shells of gas that glow when heated by the hot core they leave behind. Through a telescope, these planetary nebulae show greens from oxygen, reds from hydrogen and nitrogen, and arcs where wind met wind at different speeds. Those shells drift, cool, and mix. In time, they become part of cold clouds again. Massive stars return matter differently. Their lives are short, their ends are loud. When they explode, their shock waves sweep and crush nearby gas. In some places, the shock clears cavities. In others, it pushes clouds over the edge so gravity can take hold. The result can be new star clusters, born on the rims of old bubbles. Even a single event leaves ripples that shape many futures. Look at well-known regions and you can see steps along the loop. The Crab Nebula shows debris still moving out from a long-ago supernova, with a central pulsar feeding energy into a glowing web. The Orion Nebula shows a nursery, bright because newborn stars heat the gas around them. Pillars and knots mark where dense pockets resist erosion longest. Spectra tell the rest of the story. Which elements are present, how fast gas is moving, and how hot it is. The same tools that read a star's surface read the gas that will become new stars. Nothing is wasted. Cold clouds are patchworks made from many sources. Old supernova shells, red giant winds, quiet interstellar gas, and dust grains that grew in many places. As the mix cools, molecules form. Simple ones come first, hydrogen molecules, then carbon monoxide, water, ammonia. Dust grains help by giving molecules a surface to build on, and by blocking light that would otherwise heat and tear them apart. Chemistry in the dark is slow, but time and shelter make it rich. As clouds collapse, disks form around young stars. These disks carry the chemical record forward. Temperature drops with distance from the star. Close in, rock-forming solids can survive. Water and other ices cannot. Farther out, ices can keep their form. This makes snow lines, boundaries that separate dry and icy building zones. Over time, solids grow from dust to pebbles to boulders to planetesimals and then to planets. The proportions of rock, metal, and ice depend on where in the disk these pieces formed and how they moved. The star's light and wind shape that motion. Nearby massive stars can add heat or blast material away. Shock waves can stir the disk and leave fingerprints in its rings. The solar system holds traces of this larger neighborhood. Tiny grains in some meteorites predate the sunday. Their isotopic signatures show they formed in other stars and were mixed into the cloud that became our system. Some short-lived radioactive isotopes in early solar minerals point to a fresh supply of newly made elements nearby, likely from a dying massive star. These clues tie our origin to specific kinds of stellar endings, not a generic cloud far away. Across a galaxy, patterns emerge. Regions heavy with young stars glow blue and are rich in gas and dust. Older regions, where gas is scarce and star birth is slow, look redder and calmer. The mix of elements changes from the center to the outskirts, the so-called metallicity gradient. Near the center, where more generations have come and gone, the gas is more enriched. Farther out, the mix is closer to the simple early recipe. Star formation rates rise and fall with gas supply, pressure, and feedback from earlier stars. It is a self-regulating process. New stars heat and stir gas, which can slow further collapse. Fresh cooling or inflow from the galaxy's halo can restart the process. Even the large-scale story of the universe follows this pattern. The first stars formed when the universe was a few 100 million years old. They lit up space and helped turn neutral hydrogen back into a state where light could travel far, an era called reionization. Their supernovae seeded the next round of clouds. Later, galaxies grew by merging and by pulling in new gas along cosmic filaments. At each stage, stars added complexity and set the pace for the next stage. The time scales vary, but the logic holds. A massive star might live only a few million years from birth to blast, yet in that time it can carve a cavity tens of light years across and scatter the seeds for many more stars. A small red dwarf can shine for trillions of years, slowly building helium and keeping a steady light on its nearby worlds. Planetary systems evolve over hundreds of millions of years, with early chaos giving way to stable orbits. On a planet's surface, geologic cycles and atmospheric chemistry turn starlight into weather and into the long, slow balance that makes water last. All of this rests on the same physical rules that hold here on Earth. Gravity gathers, pressure pushes back. Heat flows from hot to cold. Light carries energy and information. Quantum rules set hard limits when matter is squeezed. Nuclear reactions follow clear paths set by mass, charge, and temperature. The numbers are large, but the ideas are familiar. A collapsing cloud heats as it shrinks for the same reason air warms in a pump. A disk flattens because spin is conserved. A star brightens slowly as helium builds in its core because denser gas must be hotter to hold the same balance against gravity. The universe is strange in its scale, not in its logic. We can read these processes because matter leaves signatures. Absorption lines in starlight reveal temperature and composition. Emission from molecules in radio and infrared bands maps cold gas in clouds. Dust glows at long wavelengths and dims background light at short ones, outlining structure. X-rays show shocks where gas is hot. Neutrinos tell us about the deepest cores at the moments of collapse. Gravitational waves reveal mergers of black holes and neutron stars in a way no light can. Each channel adds a piece. Together, they turn silence into a clear, testable story. Even the rhythm of star birth within a single cloud follows a kind of order. Turbulence, magnetic fields, and gravity set how gas breaks into clumps. The distribution of final stellar masses, the initial mass function, is similar in many places. Many small stars, fewer large ones. This bias matters. Because small stars live long and are common, they are the backbone of a galaxy's steady light. Because large stars are rare but powerful, they are the main sources of strong winds, hard radiation, and supernovae. Balance between the two keeps the cycle going. Enough feedback to stir and enrich, not so much that all gas is blasted away. planets inherit both chemistry and dynamics from their birth sites. Where rock and metal are abundant, they can build thick, iron-rich cores and silicate mantles. Where ices are common, large planets can form faster and capture hydrogen and helium envelopes. Water delivery depends on how icy bodies move inward, often guided by the gravity of growing giant planets. Traces of aluminum, 2, 6, and other short-lived isotopes in early Earth materials hint at heat sources that melted and differentiated planets quickly. All these details connect to earlier stars that finished their runs and shared their ash. The same atoms follow many roles. Carbon cycles through air, water, rock, and life. Oxygen binds to almost everything. It rusts iron, forms silicates, and fills oceans and lungs. Nitrogen builds proteins and also cools clouds as a gas. Silicon forms minerals in bedrock and circuits on boards. Sodium and potassium carry signals in nerves. Phosphorus links DNA strands and stores energy in cells. These uses exist because earlier stars made the elements and because later disks and planets concentrated them. The cycle also writes records we can check. Rings in protoplanetary disks, seen by modern radio arrays, match places where solids pile up. Isotope ratios in old stars tell how many generations came before them. Metallicity distributions in star clusters show bursts and rests in a galaxy's past. Even the faint glow of the cosmic background carries small ripples that seeded where galaxies and, much later, their stars would grow. We can place the Sun in this map as a middle-aged star born from gas already enriched by many ancestors, with planets whose composition reflects that heritage. Continuity is not smooth. There are pauses and surges. Galaxy collisions can drive gas into centers and trigger bright central engines around supermassive black holes. Starbursts can use gas quickly and then leave quiet stretches. Jets and winds can halt collapse in one region while promoting it on another's edge. But the long arc is steady. Matter cycles between stars and space, and the average mix of elements grows richer. None of this makes humans central. It does make humans typical in one important way. We are chemistry, made possible by stars and time. Minds arise on worlds that stayed stable long enough, around stars that were steady long enough, in galaxies that kept recycling material. The fact that we can name these steps means the steps left marks that any curious species could, in principle, read. The night sky is a live snapshot of this motion. Bright, blue clusters mark the places where stars are young. Red giants show where older stars swell and share their envelopes. Dark lanes trace dust where light cannot pass. Nebulae shine where gas is heated and ionized. Cold clouds go dark where they are thickest and ready to fall in on themselves. Star to cloud to star again is written there for anyone to trace with patient eyes and the right instruments. In that sense, the simple act of looking up is connected to the complex path of atoms. Light that warms a face began in a core. Dust that hit that light once was shed by a giant. The cloud that caught that dust later fell into a disk. The rock that formed from that dust later held water. The water shaped a surface. On that surface, life learned to use light. Each link uses ordinary rules, and each link is necessary for the next. When small stars end, their white dwarfs cool for eons, keeping time. When large stars end, their neutron stars and black holes hold mass and curve space, shaping orbits and lighting up gas when it comes near. All of these remnants are part of the same loop. They set boundaries and carry memory while the gas between them tries again. The cycle has run long enough to build planets with weather and biology. It will run far longer, with different mixes and different outcomes, under the same quiet rules. Astronomers read the sky like a long, careful book. Bright clusters mark places where gas has recently collapsed. Red giants show where older stars are giving back what they once held. Dark lanes trace cold dust, hiding the next pages until gravity turns them. In each galaxy, this reading reveals the same pattern: birth beside death, quiet beside fire, new light rising from older ash. The cycle is not a metaphor. It is the way matter moves. Each generation enriches the next, shifting the chemistry of the whole so that clouds cool faster, solids condense sooner, and planets have more to build with. Our own sun is one chapter in that record. It formed about 4.6 billion years ago, inside a molecular cloud that already carried heavy elements. We can see the clues in ancient minerals that locked in traces of short-lived radioisotopes, signals that a nearby massive star lived and died shortly before the solar system took shape. Earth's rocks keep part of this note. Meteorites carry the rest. Put together, they say the same thing. Earlier, stars burned, fused, exploded, and mixed their products into the raw stock that became the sun, the planets, oceans, air, and, later, living cells. The count is unknown but large. Dozens, maybe hundreds, of earlier lives fed this one. Hydrogen and helium were not enough for a wet world with mountains and biology. You need oxygen for water and breath, carbon for chains and rings, silicon for rock, iron for a core, phosphorus for DNA, calcium for bone. Those came from stars. Some were made in long, steady burns. Some were made in a final rush of heat and pressure. Some were built when neutron-rich matter from crushed stars blew apart and cooled into rare metals. The chain from cloud to planet depends on all of it. The cycle keeps galaxies active. Without it, gas would thin out and star formation would stall. With it, dying stars stir and thicken the medium, pushing and pulling clouds until gravity can act again. Shock fronts squeeze one edge while winds carve a cavity in another. The same explosion that ends a massive star lights up nearby gas, then seeds another cluster a few million years later. Seen over long spans, a galaxy breathes, gas in, stars on, gas out, stars off. Repeat. The rhythm is uneven but persistent, and each pass leaves the mix richer than before. From where we live, it is natural to treat endings as loss. Space works differently. A star's death is not erasure, it is redistribution. Material that was hot, dense, and hidden moves into space where it can cool, clump, and start again. Even the most extreme gifts find their way into the loop. Gold and platinum from neutron star mergers end up in sand and circuits and rings. Radioactive elements from ancient blasts heat young planets from the inside, driving volcanism and the slow cycling of rock and air. A galaxy is not a set of isolated lanterns. It is a community of engines that pass material forward. Stand under a dark sky and the scale can feel out of reach. Yet what you are seeing is a relay, not a gallery. Each star carries light from its own core and matter from many earlier cores. Each one is both heir and ancestor. The Milky Way is stitched together by this handoff. Thin clouds grow into stars. Stars return gas. The gas mixes and falls again. The fabric holds because every thread loops back. This continuity is the deeper legacy of stars. Their brilliance is easy to notice. Their constancy is essential. Their real gift is that they never truly waste what they borrow from gravity. The light you see tonight left a surface recently by stellar standards, but the atoms in your body began their journey long before Earth formed. In that sense, the night sky is both present tense and long memory. It shows work in progress and the records of work already done. From the first ignitions onward, stars changed the universe. Before them, space was dim and simple. With them, space became structured and varied. Photons streamed, molecules cooled, solids gathered, surfaces formed. The common thread is balance. Gravity pulling inward, energy pushing outward. For billions of years, most stars hold that balance without drama. They set the slow tempo that climates, oceans, and ecosystems need. They give enough, a long time to mean something. Patience is the lesson in their lives. A cloud collapses in steps. A proton meets another proton and waits through a chain of chances to become helium. A planet builds grain by grain in a disk. Life tries many paths under a steady lamp. Even endings take time. A white dwarf cooling, a nebula drifting apart, a shock front expanding through thin gas. The fast parts, collapses and flashes are brief because the long parts prepared them. The universe moves by layers, and stars are the steady hands that lay them down. Through those layers, stars do simple work with large results. They turn lightest elements into a toolkit. Carbon becomes the backbone of organic chemistry. Oxygen makes water and stone. Silicon and aluminum build crust. Iron sinks and makes a core that spins and shields. Phosphorus stores and transfers energy in cells. Trace metals guide reactions and shape proteins. None of this requires magic. It needs heat, pressure, time, and places where matter can travel from hot to cold and from loose to solid. If you point a telescope at a nebula, you see the nursery. If you observe a white dwarf or a neutron star, you see memory preserved. If you measure a black hole's pull, you see gravity's clean work in the absence of light. Every state is part of one story. Some are beginnings, some middles, some endings that hand off to a new beginning elsewhere. There is no single stage that explains the whole. There is a loop that does. People have always layered meaning onto that loop. The same lights that built the tools of life also guided ships and calendars and stories. Cultures drew patterns and found values in them: courage, warning, harvest, return. Modern measurements change the map, but not the pull. Knowing that Orion's belt is a trio of distant suns does not erase the hunter. It adds time and place to an old figure. Reach for the stars is still plain language for ambition, because stars still stand for what is far and steady. To feel small under the sky is normal. The spans are large and the numbers run long, but the link between us and that scale is close. The light that arrives tonight took centuries to cross space, yet the atoms in a breath took billions of years to form and travel. The same law that keeps a foot on the ground curves light near a black hole. The same fusion that warms a window-powered chlorophyll to split water and make the air. The same dust that dims the Milky Way's heart once drifted from aging stars and now lies under a boot. What science adds is a way to follow the links. Spectra reveal elements. Light curves show change. Radio maps outline cold gas. X-rays mark shocks. Neutrinos and gravitational waves carry messages from places light cannot reach in time. None of these tools replace the view from a field at night. They make that view legible. With them, astronomers can point to a faint smear and say, "This is a cloud lit by newborn stars," to a thin ring and say, "This is a disk where planets are rising," to a soft glow and say, "This is gas returning to space so that it can fall again." The picture that emerges is consistent across scales. On the level of a single cloud, turbulence and magnetism set where cores form. On the level of a galaxy, feedback from stars and central black holes sets how fast gas turns into light. On the level of the universe, the first stars started a long dawn, and their descendants still write the details. At every level, the cycle only works because matter comes back. Without return, there is no renewal. With return, there is always the next try. That is the quiet center of the story. Nothing is truly lost. Atoms change partners and roles. Energy changes form. Structures change shape. The records of those changes remain in stones, in spectra, in the background glow from the early universe, and in the chemistry of life. To stand here is to stand inside that record. To breathe is to join it. To think about it is to let the cycle become self-aware for a moment. So when you step outside at the end of the day and the first stars appear, you are watching a process that made room for you and everything you know. Some of that light began its trip before your language existed, before your species existed, before your planet cooled. Some of the atoms in you began their trip even earlier, born in places you will never see. The sky is not a stage set. It is a working ledger. It carries balance sheets of mass and light, and your name is already in the margins, written in carbon and oxygen and iron. The stars do not ask to be noticed. They keep their pace whether we look or not. Their patience gives time enough for rivers to cut valleys, for ice to come and go, for forests to spread and burn and grow again, for minds to form questions and compare notes. That patience will outlast any single world, any single species, any single habit of thought. Yet in the brief span we have, the link is close enough to feel. If there is comfort here, it is the comfort of belonging to a pattern that does not rely on luck alone. Gravity will still gather, light will still push, matter will still cycle, endings will still make means for beginnings. The first stars changed everything by turning on. Their heirs have kept the change going not loudly most of the time, but steadily, with the kind of calm work that builds durable things.